Hello everyone, and welcome to a lecture on the nodes and references implementation of a tree. So in this case, what we're going to do is define a class that has attributes for the root value, as well as the left and right subtrees, and then some methods within that class. Since this representation more closely follows object-oriented programming, or OOP, with classes in Python, we're going to continue to use this sort of representation for the remainder of the section of the course. So we won't do that list of lists representation. So just a reminder, this is the kind of tree we're going to try to implement using object-oriented programming with nodes and references. So here you can see nodes of A, B, C. You have A as your root node, and it splits off into left and right children. And let's go ahead and go implement it. Alright, so now I'm here at the Jupyter Notebook representing a tree, nodes and references. So as always, there's a reference notebook under the trees folder. This is the code we're going to be implementing here, and here's some examples of the code being used. So let's go ahead and get started. Okay. First thing we're going to do is start out with a simple class definition. So I'm just going to say class, call it binary tree, pass an object, and then start with its attributes. So the important thing to remember about this representation is that the attributes left and right will become references to other instances of the binary tree. So let's go ahead and make init, pass in self, and then I'm going to pass in, let's just call it root obj for root object. And I mentioned earlier that we sometimes call that root the key, so we'll go ahead and say self.key is equal to root obj. And as I mentioned before, we're going to have left and right attributes become references to other instances of the binary tree. So for example, when we insert a new left child into the tree, we're actually creating another instance of binary tree. In this case, we're going to just start off with no childs, or no children. So we're going to say left child equals none to start off with, and then say self.right child equals also none to start off with. Okay, so something to notice here is that the constructor function expects to get some kind of object to store in the root. Just like you can store any object you like in a list, the root object of a tree can be a reference to any object. Okay. Next, what we're going to do is look at functions we need to build the tree beyond that root node. So what I would want to do is have an insert left, and it'll take self and then some new node. And I'm actually going to put in pass here for now. And then we're also going to have an insert right, and it would also take a self new node. And we'll put a pass there. So to add a left child to the tree, we're going to create a new binary tree object and set the left attribute of the root to refer to this new object. So in order to do that, we can start filling out insert left. So I'm going to say if self.leftChild is equal to none, meaning we don't have anything there yet, what I'm going to do is say self.leftChild is equal to a new instance of binary tree. In this case, with that root node being new node. Otherwise, similarly, when we're doing the list of lists, I'm going to set an object or a variable t, have it be equal to a binary tree with new node, and say t left child is equal to the self.leftChild. And then say self.leftChild is then equal to t. Alright, let's go ahead and break down what this code is actually doing on the insert left. We're going to have to consider two cases for insertion. The first case is going to be characterized by a node with no existing left child. So self.leftChild is equal to none. When there's no left child, we're just simply adding a node to the tree. The second case is going to be characterized by a node with an existing left child, that else. So in the second case, we insert a node and push the existing child down one level in the tree. The second case is handled by that else statement. So make sure you review this and make sure you understand what's actually going on. First case, there's no left child, so we're simply adding a node to that tree. Second case, we have a node with an existing left child, so we insert a node and push the existing child down one level in the tree. So the code for insert right is going to consider a symmetric set of cases. There will be either no right child, or we must insert the node between the root and an existing right child. So let's go ahead and code that out. It's going to be really similar. I'm going to say if self.rightChild is equal to none, then we just insert that node. Right child is equal to an instance of binary tree with new node. And then we're going to say else t is equal to binary tree with that new node. Remember, we're going to push it down one, so we're going to say t right child. Let me scroll over. T right child is equal to self dot right child. Then finally, set self dot right child equal to t. Reason for doing this is that so you don't accidentally overwrite something before you set it. Okay, so now to round out the definition for a simple binary tree data structure, we're going to write some methods that allow us to access things, such as the right and left children, as well as the root nodes. So this will just be 4 methods. Let's get some space here. I'm going to say get right child self, and then I'm going to return self dot right child. So that makes sense if we get the right child. Similarly, I'm going to do the same for the left child. So get left child calls self, and then it just returns self dot left child. I also want 2 functions for setting the root value and getting the root value. So for setting the root value, we'll just call it set root val. And it's actually going to need to take some object to set the new root value, and then we're going to say self.key is equal to that object that you pass. And then lastly, to get the root value, get root val, we just need to pass in self, and we're just going to return self.key. Okay, so let's go ahead and quickly review what we just did. We have our class binary tree. We start off with the attributes, set the key or equal to that root object, that root node, no children to start off with, and then we have 2 basically symmetrical methods for inserting left and right nodes. And you can see that we check if there's something there. If there isn't, we just set it equal to the new binary tree. Otherwise, we're going to push it down to the new level. And then we have 4 methods for getting and retrieving children, and also getting and retrieving root values. So let's go ahead and make a simple tree to show how this can work. First thing we're going to do is set R equal to an instance of binary tree, and we're going to set a string A. Whoops. Got an error here, and that's because I forgot to write this correctly. Sorry about that. Okay, so now everything's working. Remember, if you ever have 2 double underscores in Python, you also need to close them out. All right, going down, we have our binary tree R, so let's go ahead and just start off by getting that root value. So I can say by tab, get root val. Let's go ahead and close parentheses so we actually get something returned. All right, and there we have that root value. So if we say get child, such as left child, we shouldn't actually get anything, so that's a none. So if we actually print this out, you'll notice it turns none up. All right, so let's go ahead and try inserting a left child. So I'm going to say r dot insert left, call it b. So we've inserted something to the left. So if I say r dot get left child, you'll notice something interesting happens here. Remember, we actually get another instance of that binary tree. So what I could do is then call roots off of this. So I can say then get root value, and then that's how we get b. So with this nodes and reference systems, you're referring to subtrees again. So you have your main tree and then subtrees within it, which is why when you just call that left child, you got an instance of that binary tree. All right, so that's it for the basic implementation using nodes and references. What I encourage you to do is try to build out your own tree. So write a tree down, just a simple one on a piece of paper, and then see if using this implementation, you can actually code it out and insert the children correctly. All right, that's it for this lecture. I'll see you at the next one. Thank you.